The SMEE SSI 800-10W arrived at SMIC sometime around early 2025, a domestic immersion scanner made in China built to expose silicon wafers with a 193 nanometer argon-fluoride light source and delivered without an ASML logo anywhere on its chassis. The surface layer of this machine is a headline, and the headline is accurate as far as it goes. The deeper you cut into its architecture, its measured performance, and the industrial timeline surrounding it, the more precisely you can locate what it actually is and what it is not yet. This is a layer-by-layer dissection of one machine. The thesis is not that China has failed or that China has succeeded. The thesis is that a lithography tool built under restriction carries the geometry of that restriction in every design choice it makes, and that the SSA 800-10W is a readable object, real, precisely bounded and legible at every depth. 5 cuts: the machine itself, its measured resolution, and what multi-patterning does with it, the production timeline that governs when any of this matters at scale, the parallel track ecosystem growing around it, and finally the deepest layer, the constraint that export controls pressed into the silicon before the first wafer was ever loaded. The outermost layer of the SSA 800-10W is its optical identity. This is an immersion deep ultraviolet scanner, meaning it uses a liquid medium, ultra-pure water, between the final lens element and the wafer surface to shorten the effective wavelength and increase the numerical aperture of the optical system. The light source operates at 193 nanometers in the argon-fluoride band. That combination, immersion medium, 193 nanometer wavelength refractive optics, defines a platform that ASML, Nikon, and Canon developed through the 1990s and 2000s, and that became the workhorse of the global semiconductor industry for the 65 nanometer through 28 nanometer generations. SMEE did not invent this architecture. The company inherited the physics and built toward it, and the SSA 800-10W represents SMEE's most advanced publicly acknowledged tool as of early 2025. Delivery to SMIC, China's leading domestic foundry, was reported around that period, making this the first credible domestic immersion scanner to reach a production environment. These are company claims and reported delivery facts. Independent third-party validation of the full specification set has not been published. The reason this machine uses argon-fluoride immersion rather than extreme ultraviolet is not a design preference. Extreme ultraviolet scanners require components that are either controlled under export regulations or have not yet been developed domestically. A 13.5 nanometer light source of sufficient power, multi-layer reflective optics manufactured to atomic level tolerances, a pellicle infrastructure capable of surviving the photon flux at that wavelength, and a vacuum environment throughout the optical path. The entire extreme ultraviolet supply chain is concentrated in a small number of suppliers, most of them in countries that have aligned their export policies with the United States restrictions applied beginning in earnest in 2022. The argon-fluoride immersion platform, by contrast, relies on physics that are decades old and on components whose sourcing is broader. SMEE built what it could build. The machine on the bench is the result. The choice of wavelength is the first readable trace of the constraint, visible before you open a single panel. The first interior layer is the machine's measured performance, and the number that matters most here is overlay accuracy. Overlay accuracy is the precision with which the scanner aligns each successive exposure passed to the one before it on the same wafer. SMEE's own claims place this figure at approximately 1.9 nanometers. At that level of precision, the machine is positioned, according to the company's own specification, to support multi-patterning processes capable of reaching roughly the 11 nanometer class. No independent benchmark confirming this overlay figure across production conditions has been published as of the time of delivery. Multi-patterning is the technique that extends a 193 nanometer light source far below what the wavelength alone could resolve. The principle operates by dividing a single circuit layer across multiple exposure passes, each slightly offset from the last, so that the interference of those passes produces features smaller than any single pass could generate independently. ASML's customers, TSMC, Samsung, Intel, used quadruple patterning to push 193 nanometer argon-fluoride immersion tools into 10 nanometer and even 7 nanometer class production before extreme ultraviolet became available at scale. SMEE is pursuing the same extension on its own platform. What makes the overlay figure the structural rate limiter is that multi-patterning is only as precise as the machine's ability to align each pass to the preceding one. If the overlay drifts by even a fraction of a nanometer between passes, the interference patterns shift and the effective feature size degrades along with it. Each additional exposure pass compounds the alignment requirement rather than relaxing it. Consider what this means physically. A single circuit layer that would be printed in one pass on an extreme ultraviolet scanner must instead be divided across 4 passes on an argon-fluoride immersion tool, with each pass landing within roughly 1.9 nanometers of where the previous pass ended. That alignment must be maintained not just once on a single demonstration wafer, but continuously across a full production lot. Thousands of wafers run over days of continuous operation under thermal load as the tool's stage and optics expand and contract with heat. The 1.9 nanometer overlay claim is SMEE's statement of what the machine can achieve. The overlay stability across a production lot over time, the variance figure that a process engineer actually needs before committing a product to a tool, has not been independently confirmed. That gap between specification and demonstrated production stability is the tension this layer leaves open. The timeline layer sits one cut deeper, and it contains a structural fact that reshapes how the resolution numbers should be read. Volume production using the SSA 800-10W is not expected before approximately 2027, based on analyst estimates and industry reporting at the time of delivery. The machine was delivered around early 2025. That interval, roughly 2 years between delivery and anticipated production readiness, is consistent with the maturation timelines observed for new lithography platforms from established manufacturers, including ASML. The difference here is what fills that interval for a first-generation domestic tool. When a leading foundry integrates a new lithography tool from ASML, it integrates a machine with a documented service history, a global installed base of hundreds of comparable systems, and decades of accumulated process recipes optimized for that tool's specific optical behavior. Field service engineers with deep institutional knowledge of the platform are available. The process qualification draws on a body of prior work that compressed the timeline for each successive tool generation. None of that infrastructure exists for the SSA 800-10W. The engineers at SMIC integrating this tool are working with a machine that has no comparable installed base to reference, no established process ecosystem, and no external service network with experience on the specific optical and mechanical characteristics of this particular scanner. The qualification period must build that knowledge from near zero. 2 years is a realistic estimate for that construction. It is also the period during which the leading edge continues to move. The leading edge in 2025 sits at the 3 nanometer class in high volume production. By 2027, when the SSA 800-10W is projected to begin contributing to commercial output, 2 nanometer class production is expected to be underway at TSMC. The SSA 800-10W's anticipated production capability, roughly 11 nanometer class through multi-patterning, places it approximately 4 to 5 process generations behind the frontier at the moment it first ships commercial silicon. That distance is not a judgment about the quality of SMEE's engineering. It is a physical description of where this machine sits in the global production landscape, measured in process generations and in time. The position is readable from the delivery date and the projected production date together. Neither number alone contains the full fact. The interval between them is the layer. The next layer down reveals that the SSA 800-10W is not the only domestic immersion scanner under development. A startup identified as Yuliangsheng has been reported as pursuing its own domestic immersion deep ultraviolet scanner, representing a second development track running in parallel with SMEE's program. The company's reported development status suggests it is at an earlier stage than SMEE's delivered tool. Domestic sub-10 nanometer lithography capability, whether from SMEE, Yuliangsheng, or another entrant, is not expected before roughly 2030 based on analyst projections. These timelines are projections, not confirmed engineering schedules or production commitments from either company. The structural significance of the parallel track arrangement is not that it doubles the output. It is that it distributes the risk and accelerates the accumulation of institutional knowledge across a larger engineering population. A single state-directed program concentrated in one vendor is vulnerable to a fundamental limitation at the vendor. If SMEE's platform encounters a constraint it cannot engineer around, the program has no alternative path. A parallel track structure, two organizations developing competing or complementary approaches under broadly similar constraints, means that a dead end encountered by one track does not stop the other, and that insights developed on one track can migrate. The teardown analysis suggests this is less a redundancy than a deliberate architectural choice for the domestic program as a whole, consistent with how China has accelerated in other hardware domains where it moved faster than early projections suggested. What the parallel track structure cannot guarantee is the resolution of the deeper dependency. The sub-10 nanometer projection rests on assumptions about progress not only in optical engineering, but in the precision component base that lithography tools require regardless of their wavelength. Vibration isolation systems capable of maintaining stage position to sub-nanometer tolerances, wafer stage positioning hardware with the repeatability to sustain multi-patterning alignment across a production run, and laser source components for the argon-fluoride band that meet the power and coherence requirements for high-throughput production. Those components currently have limited domestic supply in China. Whether Yuliangsheng's parallel track closes any of those gaps by 2030, or whether additional supply chain constraints extend the timeline, is a question the dissection cannot answer from the outside. The deepest cut reaches the layer the outer shell does not announce. The architecture of the SSA 800-10W, its choice of 193 nanometer argon-fluoride immersion, its reliance on multi-patterning to extend effective resolution, the 2-year interval between delivery and production readiness, and the parallel track ecosystem being built around it, is the geometric consequence of the export control architecture applied to advanced semiconductor manufacturing equipment by the United States, the Netherlands, and Japan beginning in earnest in 2022 and tightened in subsequent rounds. ASML's extreme ultraviolet scanners are controlled under Dutch export regulations and cannot be exported to China. The high numerical aperture extreme ultraviolet systems that represent the current leading edge of ASML's product line were never available to Chinese customers under any licensing regime. The restriction did not stop SMEE's program. It shaped the program's trajectory at every layer. SMEE's engineers did not choose argon-fluoride immersion because they preferred it to extreme ultraviolet. They chose it because extreme ultraviolet's enabling components, the 13.5 nanometer light source, the multi-layer reflective optics that must be manufactured to atomic level precision, the pellicle infrastructure, the full vacuum optical path, are either tightly controlled under export regulations or not yet available from domestic suppliers. The argon-fluoride immersion platform is the architecture that remained reachable because its core physics predate the tightest controls and its supply chain has broader international sourcing options than extreme ultraviolet's bespoke component set. Multi-patterning is the extension technique that allows a controlled wavelength to reach below what the wavelength alone permits, and it does so without requiring the components that are most tightly controlled. It is the engineering path that remains open when the more direct path is closed. The 2027 production timeline reflects the maturation period for a tool built without the institutional support of a global installed base and without the process ecosystem that decades of ASML deployment created at leading foundries. The overlay figure, the wavelength, the production schedule, the parallel track structure, every layer of this machine, opened and examined, carries the imprint of the restriction that surrounded its development. What teardown reports and analyst notes describe is the machine's specifications compared to ASML's. What they do not state outright is that the gap between the SSA 800-10W and the leading edge is not primarily an engineering gap. It is a materials and supply chain gap, shaped by policy and made durable by the concentration of extreme ultraviolets enabling components in a small number of suppliers operating under aligned export regimes. SMEE's engineers are skilled enough to have built a real immersion scanner. The constraint is not their ceiling. It is the perimeter inside which they are building. The machine's architecture is a map of what was reachable within that perimeter. Reading that map is the anatomist's actual task. 3 things this dissection cannot settle: The overlay accuracy figure of approximately 1.9 nanometers is SMEE's own claim. No independent metrology report or third-party process qualification has been published confirming this figure under sustained production conditions. The difference between a specification achieved in a controlled demonstration and a specification maintained across a full production lot over weeks of continuous operation is the difference between a performance claim and a process capability. The dissection cannot determine which of those this figure represents. The 11 nanometer class capability attributed to the machine through multi-patterning is a resolution claim, not a yield claim. Multi-patterning at 4 passes is sensitive to overlay drift, focus uniformity, and wafer stage repeatability in ways that compound across each additional pass. A tool can demonstrate the resolution target on a single wafer under optimal conditions and still produce commercially unacceptable yield when the process is run continuously at volume. No yield data from SMIC's integration work with this tool has been published, and the projection that domestic sub-10 nanometer lithography capability will not arrive before roughly 2030 rests on assumptions about development pace, component availability, and the absence of further export control tightening, any of which can shift the timeline in either direction. The SSA 800-10W is a real tool with a real delivered overlay specification, a real production destination, and a real timeline placing its commercial contribution roughly 2 years out from delivery. What the dissection cannot settle is whether the specification holds at production yield, whether the multi-patterning extension reaches the claimed node class under continuous operation, and whether the ecosystem around it develops fast enough to close the remaining gap before 2030. The sample is consistent and readable. What it does not show is proof of production yield, independent metrology, or a confirmed development roadmap for the next generation. The SSA 800-10W, taken apart layer by layer, is evidence of 2 things simultaneously. It is evidence that China has built a real lithography tool, an immersion scanner with a credible overlay specification, delivered to a leading foundry, positioned to reach the 11 nanometer class through multi-patterning, and on track to begin contributing to commercial production around 2027. And it is evident that the restriction shaped the tool at every layer. The choice of wavelength, the reliance on multi-patterning extension, the production timeline, and the parallel track ecosystem being assembled around it are all consequences of a perimeter drawn by export controls applied to extreme ultraviolet and its enabling components. The machine is an answer to a defined set of constraints. The answer is real. Whether it is sufficient, and by what standard sufficiency is measured for what product in what year, is the question the machine itself cannot answer. Cut deep enough into the SSA 800-10W, and you find the buried fact the thesis placed on the table at the start. The restriction that was meant to contain this program is the reason its inner layers look exactly the way they do. The constraint is not context, it is structure. It is present in the silicon. What this machine proves is that a perimeter drawn in policy produces, in time, an object whose architecture is the trace of that perimeter, and that the object, once built, begins to close the distance the perimeter was drawn to preserve. There is another object worth putting on this bench, the domestic resist materials and deposition equipment that multi-patterning at this level depends on, because the lithography tool is only one layer of a process stack, and the layers beneath it have their own anatomy. Tell us in the comments which layer you want to open next. If this kind of dissection is useful to you, subscribe. There are more objects on the bench.